right, so we're going to talk about resonance structures. There's a specific subset of Lewis structures, and you probably are going to want to know a little bit about formal charge before we get into this, but if you haven't seen that lecture yet, it's okay. This will still make sense. So here we go. Our lesson objectives will define what resonance is. We'll give examples of Lewis structures with resonance, and we will write the resonance structure for an inorganic compound. All right, so what is a resonance structure? What is resonance? Well, resonance occurs when you have an either or decision to make when you add a double bond to the Lewis structure. So you end up making resonance structures. When you have an either or decision, it is all of them at the same time. Yes, that is weird, but it's all of them at the same time. Resonance structures have delocalized electrons. So it is in reality that they are in each location simultaneously. Remember that electrons are represented by probability functions, so this is not as strange as it seems. Okay, quantum mechanics is strange, but if you take those ideas to be correct, then the idea that electrons are in all of those locations at once is not actually that odd. Now, single bonds are the longest, and triple bonds are the shortest when we're talking about bond length, going from one nucleus to the other. The shorter the bond, the stronger the bond. So a triple bond is stronger than a single bond, which makes sense. You're sharing 6 electrons. Anyway, in a resonance structure, it has a bond length that is shorter than a single bond, but not longer than a double bond. So it's somewhere in between, which is kind of what you would expect if you are, in fact, sharing those electrons, which you are. Delocalized charge is actually favorable. So when we can make a resonance structure, that makes for a more stable structure. All right, let's try an example. We have carbonate ions. So we count the valence electrons. We have 6 times 3, which gives us 18 for carbon for oxygen, plus 4 for carbon, plus 2 for the charge on our carbonate ion, for a total of 24 valence electrons. And if we do step 1 through 4 on our Lewis structures, we get to this particular structure. And you'll notice that I have the brackets because I've got a charge. All right, to get an octet on that carbon, we've got to take 2 electrons from one of the oxygens with the lone pair, but which one do we take it from? So when we have an either or option, it's all of them. So how will this look? We have 3 equivalent representations of the same ion here. If you put a double-sided arrow between each structure to show that they are all in existence at once, this is the resonance structure for the carbonate ion. The delocalized charge makes this structure more stable than if the charges were not delocalized. Okay, so you'll write all the possibilities and you'll put arrows between them to represent a resonance structure. But what about inorganic molecules? So a lot of organic molecules do in fact have resonance, but we don't have the luxury of a single central atom when we're talking about organic structures. So let's talk about the benzene ring, because this is actually really freaking common. In the benzene ring, every other bond is a double bond. When organic chemists write this in a reaction, they may use either of the following representations. So on the bottom right-hand corner there, we have a circle in the middle to indicate that all of that charge is delocalized, or you have dotted lines, which means the same thing. So these are equivalent representations, and organic molecules, we will often see this type of imagery. And what it means is we've got every other bond as a double bond. Now, we do have other types of resonance. I'm simply representing one that has a different image in the line structure because this is an opportunity to show what that would be. But every organic compound pretty much is going to be more complicated than a single central atom. So you're going to have either or options on where to place a double bond, but when you do use them, you will have multiple different centers where you could move those electrons instead of just having a central atom and multiple places to put the double bond, and you may be able to move that around onto other central atoms. To summarize, resonance structures occur when you have an either-or option of where to put a double bond. Resonance bonds are all the same length when measured and are between the length of a single and double bond. We write each possible structure and put double arrows between them to represent the Lewis structures for these compounds. And finally, resonance imparts stability because sharing the electrons, delocalizing them, means lower energy level overall for the compound.